Hi and welcome to John's Maths book. In this video, we're going to be looking at solving first-order differential equations by separation of variables and finding the particular solution. If you like the video, please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. When solving differential equations, sometimes we are given initial values which allows us to find a particular solution of a differential equation. This allows us to find a unique function at the initial value or values by replacing the arbitrary constants in the general solution. The number of initial values we need is equivalent to the order of the differential equation. In the following examples, we're going to solve some first-order differential equations with an initial value by the separation of variables technique which we learnt in an earlier video. So in this first example, we're going to solve the differential equation dy by dx is equal to x divided by y squared, where we're given an initial value where y is equal to 1 and x is equal to 0. To separate the variables, we need to get the differential equation into the form of dy by dx is equal to some function of x multiplied by some function of y. In this example, f of x is equal to x and g of y is equal to 1 divided by y squared. If we now separate the variables by taking y squared over to the left-hand side of the equation and dx over to the right-hand side of the equation, we're left with y squared multiplied by dy is equal to x multiplied by dx. We can now integrate both sides of this equation to give the general solution of the differential equation. On the left-hand side of the equation, the antiderivative of y squared is y cubed divided by 3 plus a constant of integration. Let's call that c1. And on the right-hand side of the equation, the antiderivative of x is x squared divided by 2 plus a constant of integration. Let's call that c2. If we now subtract constant c1 from both sides of the equation, and let c3 equal c2 minus c1, we're left with y cubed divided by 3 is equal to x squared divided by 2 plus c3. Multiplying both sides of the equation by 3 and letting c equal 3 times c3, we're left with y cubed equals 3x squared divided by 2 plus c. Taking the cubed root of both sides of the equation, we're left with a general solution of y is equal to the cube root of 3 times x squared divided by 2 plus c. If we now substitute in our initial condition of y equals 1 at the point x equals 0, we're left with y is equal to the cube root of 3 times 0 divided by 2 plus a constant c. Simplifying this, 1 is equal to the cube root of c, and therefore c is equal to 1. And now plug in our value for c back into the general solution, we're left with a particular solution of y is equal to the cube root of 3x squared divided by 2 plus 1. In this example, we're going to find the particular solution of the first order differential equation dy by dx is equal to e to the x divided by y at the point y is equal to minus 4 and x is equal to 0. We can use a technique of separation of variables to solve this differential equation by moving all terms involving y to the left-hand side of the equation and all terms involving x to the right-hand side of the equation. So when we do this, we're left with the equation y multiplied by dy is equal to e to the x multiplied by dx. Now we can integrate both sides of the equation. The antiderivative of y is y squared divided by 2 plus a constant of integration which we can call c1. The antiderivative of e to the x is e to the x plus a constant of integration. Let's call that c2. If we now manipulate this equation algebraically and let c equal c2 minus c1, we're left with y squared is equal to 2 times, and in the bracket we have e to the power of x plus c. Taking the square root of both sides, we're left with a general solution of y is equal to plus or minus the square root of 2 times e to the power of x plus c. To find the particular solution of this differential equation, we can use our initial value of y is equal to minus 4 where x is equal to 0 and plug these values into our general solution. This leaves us with minus 4 squared equals 2 into the bracket of e to the power of 0 plus a constant c. If we now expand this out, we've got minus 4 squared is 16, which is equal to 2 times e to the power of 0, which is 1, plus 2 times the constant c. Dividing both left and right hand side by 2 and subtracting 1 from both sides, we're left with c is equal to a value of 7. If we now plug this value of c into our general solution and take the negative square root, because we know that y is a negative value, we're left with y is equal to minus the square root of 2 times and into the bracket e to the x plus 7. And this gives us our particular solution.